Hello everyone. We are pleased to present our joint research titled Methods and Tools for Automated Adaptive Traffic Light Control based on Computer Vision. This work was carried out by Vasyl, Iryna, Gado, Bohdan, Fylypchuk, and Andrei Koval from Lviv Polytechnic National University. In this project, we propose a novel vision-based system for adaptive traffic signal regulation grounded in formal modeling and engineered for real-time responsiveness in constrained urban environments. Urban areas are facing growing problems related to traffic congestion, delays, and increased air pollution. Fixed timer traffic lights are inadequate for today's dynamic conditions, and existing adaptive systems are often expensive, infrastructure-heavy, and not scalable in countries like Ukraine, especially under wartime pressure. We address this with a lightweight, vision-based approach that combines real-time adaptation with practical deployment feasibility. Our objective is to develop a scientifically grounded model for automated adaptive traffic light control based on computer vision. The system detects vehicles in real time using a deep learning YOLO model, determines the optimal green phase duration through a formal algorithm, and sends control commands with low latency via WebSocket. Rather than relying on simple rules or reactive behaviors, we focus on structured decision making and continuous real-time responsiveness, which together form a consistent and adaptive control strategy. Our key contribution is a mathematical model for dynamically allocating green light time based on vehicle counts, constrained by configurable thresholds. We also propose a hybrid distributed architecture that blends Python-based AI detection with deterministic .NET backend logic. The system is containerized and modular, with WebSocket as a primary communication layer and automatic fallback to HTTP, ensuring robustness under network instability. Traditional systems like SCATS, the Sydney Coordinated Adaptive Traffic System, and SCOOT, the Split Cycle Offset Optimization Technique, rely on inductive sensors and predefined logic. These solutions are often costly, rigid, and challenging to adapt or scale. Meanwhile, open-source alternatives typically emphasize detection but lack robust decision-making infrastructure or formalized control models. In contrast, our system integrates high-precision vehicle detection with flexible, configurable logic and reliable two-way communication, resulting in a hybrid architecture that offers both scientific novelty and practical value. Here's how the system works. Live video feeds from traffic cameras are processed by the YOLO detector, which extracts vehicle counts. The data is sent via WebSocket or HTTP to a .NET-based decision engine that computes the appropriate green light duration. Traffic signals are updated accordingly. The message with the green light duration for the current cycle is sent via WebSocket to the client, responsible for controlling the traffic light at the given intersection. For administrators, there is an admin panel where users can monitor and reconfigure the system through a web interface built in React. All components are modular and run in Docker containers for easy scaling and deployment. We used Python for Vision module and YOLO version 11 for real-time object detection. The backend is built with .NET Core and handles decision logic and API access. React powers the admin panel, and WebSocket is used for real-time communication. Detection logic filters out unreliable outputs by applying a confidence threshold. Only objects detected with a confidence score of 0.7 or higher are considered valid. This improves the overall accuracy of the system. All valid detections within a video frame are counted, producing a real-time vehicle count that serves as input for determining the green phase duration. If this count corresponds to a value in the configuration table, that predefined duration is applied. If not, the system calculates the duration by multiplying the vehicle count by a standard time per vehicle parameter. To ensure the result remains within safe operating limits, the final green time is clamped between administrator-defined minimum and maximum bounds. At the heart of our system lies a continuous data-driven control loop. YOLO version 11 processes the video frames, and a message with vehicle count, camera ID, and timestamp is sent to the backend via WebSocket or HTTP request. This real-time loop forms the core of our detection process. The system consists of four core components: the client-side detection module, the backend decision logic, the administrative web interface, and the database. Real-time communication between the detection module and the backend, as well as between the backend and the traffic light controller, is implemented via WebSocket to minimize latency. In case the WebSocket connection fails, the detection module automatically falls back to HTTP to preserve system continuity. The admin interface communicates with the backend exclusively over HTTP. This architecture ensures performance and reliability for critical operations while maintaining simplicity in administrative functions. The modular structure supports easy scaling and future extensibility. We tested the system using real-time data in a simulated environment. WebSocket consistently showed lower and more stable latency than HTTP, which remained acceptable as a fallback. These results validate our communication approach for real-time systems. There are, of course, some limitations. The system depends on a stable connection between the detection and backend modules. WebSocket interruptions must be handled reliably. Scaling to larger networks may require additional optimization on the server side, but our design already anticipates that through containerization and service isolation. Looking ahead, we plan to integrate pedestrian detection to improve inclusivity, particularly for people with mobility challenges. We also plan to extend the system with modules for traffic forecasting and integration with smart city platforms. The architecture supports such expansion without reworking the core logic. To conclude, our system presents a lightweight, scalable, and adaptive solution for traffic light control. It integrates real-time vehicle detection with responsive decision-making, ensuring both accuracy and efficiency. The hybrid architecture combines the flexibility of AI-based detection with the robustness of a structured backend engine, delivering the best of both approaches. With the modular design and reliable fallback mechanism, the system is ready for a pilot deployment in urban environments and provides a solid basis for continued scientific exploration. Thank you for your attention.